What if everything we've been taught about atoms is completely wrong? What if the very foundation of modern physics, the particles that make up everything around us, don't actually exist the way we think they do? In Richard Feynman's last major interview before his death, one of the greatest minds in physics made statements that seem to contradict the very science he helped build. And if you stick around, you're going to understand why his final words might change how you see reality itself. Make sure to hit that subscribe button because we're diving deep into one of the most mind-bending mysteries in physics. Richard Feynman wasn't just any physicist. This was a man who worked on the Manhattan Project, won the Nobel Prize, and revolutionized quantum mechanics with his famous Feynman diagrams. He was known for his ability to explain complex ideas in simple terms, and more importantly, for his radical honesty about what we actually know versus what we pretend to understand. When Feynman talked, the entire scientific community listened. So when he gave his final interview in the late 1980s, struggling with the cancer that would eventually take his life, his words carried enormous weight. In that interview, Feynman said something that shocked even his closest colleagues. He admitted that nobody actually understands quantum mechanics, but he went further than that. He suggested that our entire conception of particles, of atoms, of the fundamental building blocks of reality might be nothing more than useful fiction, a mathematical tool that works for predictions but doesn't represent what's actually there. Think about that for a moment. The man who helped create modern atomic theory was telling us that atoms might not be what we think they are at all. Let's back up and talk about what we've been taught. In school, you probably saw a picture of an atom, a nucleus in the center with protons and neutrons and electrons orbiting around it like tiny planets around a sun. It's a neat, clean picture. It makes sense. You can visualize it. The problem is, according to Feynman and the actual mathematics of quantum mechanics, this picture is absolutely wrong. It's not just simplified, it's fundamentally misleading about the nature of reality. The first contradiction Feynman pointed out is the wave-particle duality. Electrons aren't little balls orbiting the nucleus. They're not really particles at all, and they're not really waves either. They're something else entirely, something we don't have good words for in human language. When we're not looking at an electron, it exists in what's called a superposition, spread out like a cloud of probability. It doesn't have a definite position until we measure it. And here's the really weird part that Feynman emphasized in his last interview. The act of measuring it, of observing it, actually brings it into existence in a specific location. This isn't just philosophical mumbo-jumbo. This is what the mathematics actually tells us. Feynman spent years developing the path integral formulation of quantum mechanics, which suggests that a particle traveling from point A to point B doesn't take one path. It takes every possible path simultaneously, including paths that go backward in time, paths that loop around, paths that seem to violate everything we know about how objects should move. Only when we observe the particle do all these possibilities collapse into one actual path. Now here's where Feynman's final interview gets really interesting. He was asked whether particles are real things that exist out there in the world. His answer was uncomfortable and honest. He said we have to be very careful about what we mean by real. The equations work. We can predict what will happen in experiments with incredible accuracy. But that doesn't mean the particles exist as little objects sitting in space. They might just be useful concepts, ways of organizing our observations that don't correspond to anything physical at all. Think about what this means for atoms. An atom isn't a tiny solar system. It's not a solid object you could hold if you had small enough fingers. According to quantum mechanics and according to Feynman's interpretation, an atom is more like a fuzzy cloud of probability, a set of mathematical relationships that tells us what we're likely to observe if we look. But when we're not looking, it might not have definite properties at all. It might not be anywhere in particular or have any particular characteristics. Feynman gave an example that really drives this home. He talked about the double-slit experiment, which you might have heard of. You shoot electrons one at a time through two slits, and somehow each individual electron interferes with itself, creating a pattern that only makes sense if the electron went through both slits at once. When you try to observe which slit it goes through, the interference pattern disappears. The electron starts behaving like a normal particle. It's as if reality itself changes based on whether we're watching. In his last interview, Feynman admitted this bothered him his entire life. He said anyone who claims they understand this is lying. The mathematics works perfectly. The predictions are accurate to an absurd number of decimal places. But what it means about the actual nature of reality remains deeply mysterious. And he suggested that maybe we're asking the wrong question when we ask what particles really are. Maybe reality at the quantum level doesn't work like reality at our scale, and trying to picture it leads us astray. This brings us to another contradiction Feynman discussed: the idea of position and momentum. Where classical physics says objects have both a position and a momentum at every moment. You can know where something is and how fast it's moving. But Heisenberg's uncertainty principle, which Feynman helped refine, says this is fundamentally impossible for quantum particles. The more precisely you know position, the less precisely you can know momentum, and vice versa. This isn't a measurement problem. It's not that our instruments aren't good enough. It's that the particle literally doesn't have both properties at the same time. Feynman explained this in his interview with a thought experiment. Imagine trying to measure an electron's position very precisely. To do that, you need to bounce light off it. But light carries momentum, and when the photon hits the electron, it changes the electron's momentum in an unpredictable way. You might think we just need gentler light, lower energy photons. But lower energy means longer wavelength, which means less precision in measuring position. There's a fundamental trade-off built into the universe itself. Nature prevents us from knowing both properties simultaneously. But here's the really radical part of what Feynman was saying. He suggested that it's not just that we can't know both properties, it's that the electron doesn't have both properties. Before we measure it, position and momentum are undefined, existing only as probabilities. The electron isn't hiding its true position from us. It genuinely doesn't have one until we force it to by measuring. This is what Feynman meant when he contradicted our everyday understanding of atoms. The particles that make up atoms don't have definite properties until we observe them. Now let's talk about what Feynman called the most profound contradiction of all: quantum entanglement. When two particles interact, they can become entangled, meaning their properties become correlated in ways that transcend space and time. If you measure one particle and find it spinning clockwise, the other particle, no matter how far away, will instantly be spinning counterclockwise. Einstein called this spooky action at a distance and thought it proved quantum mechanics was incomplete. There had to be hidden variables determining the outcome. But experiments have confirmed quantum mechanics is right, and Einstein was wrong. Feynman discussed these experiments in his last interview with a sense of awe and discomfort. The particles don't have predetermined spins. They're in superposition until measured. Yet somehow, measuring one instantly affects the other across any distance. This seems to violate relativity, which says nothing can travel faster than light. Feynman's resolution was deeply unsettling. He suggested that at the quantum level, space and time might not work the way we think. Distant particles might not actually be separate things. This gets at the heart of what Feynman was really saying about atoms. When we think of an atom as a collection of separate particles, protons and neutrons in the nucleus, electrons around it, we're importing classical concepts that don't apply. At the quantum level, the whole atom is one interconnected system. You can't really separate the electron from the nucleus. They're entangled, part of one quantum state. The boundaries between things that seem so obvious at our scale dissolve when you look closely enough. Feynman also talked about virtual particles, another concept that contradicts our intuitive understanding of atoms. According to quantum field theory, which Feynman helped develop, empty space isn't actually empty. It's seething with particles and antiparticles popping in and out of existence, borrowing energy from the vacuum for brief moments before annihilating each other. These aren't real particles in the sense that they can't be directly observed, but they have real effects. They change the energy levels of atoms in ways we can measure. So the space between the nucleus and the electrons in an atom isn't empty. It's filled with this quantum foam of virtual particles, and the electrons themselves are constantly emitting and reabsorbing virtual photons. What we call an electron is really an electron surrounded by a cloud of virtual particles that pop in and out of existence. This cloud is part of what gives the electron its properties, like its mass and charge. The particle we think of as fundamental is actually a complex system of interactions with the quantum vacuum. In his final interview, Feynman emphasized how strange this makes the concept of an elementary particle. If the electron is constantly interacting with virtual particles, constantly absorbing and emitting them, in what sense is it elementary? In what sense is it even one thing, rather than a process, an ongoing interaction with the fields that fill all of space? He suggested that our language and concepts are inadequate. Here we talk about particles because it's convenient, but what's really there might be better described as excitations in quantum fields. This brings us to quantum field theory, the framework Feynman helped create. In this view, particles aren't fundamental at all. What's fundamental are fields that fill all of space: the electromagnetic field, the electron field, the quark fields. Particles are just localized vibrations in these fields, like waves on an ocean. An electron is a ripple in the electron field. A photon is a ripple in the electromagnetic field. When particles are created or destroyed, it's really just the fields changing their state of excitation. Feynman explained in his interview that this resolves some paradoxes but creates new ones. It explains how particles can be created and destroyed. So something that doesn't make sense if particles are fundamental objects. But it makes the concept of an individual particle even more problematic. If an electron is just a wave in a field that extends throughout the universe, in what sense is it localized? In what sense is it different from other electrons? Feynman suggested that the identity of particles is another classical concept that breaks down at the quantum level. Here's something that will really bake your noodle. Feynman showed that antimatter is mathematically equivalent to matter moving backward in time. In his diagrams, you can draw an electron moving forward in time, or a positron, the electron's antiparticle, moving backward in time, and the mathematics is identical. He even speculated that all electrons in the universe might be the same electron. zigzagging back and forth through time. While he admitted this was probably not literally true, the fact that the mathematics allows it shows how weird quantum reality is. The implications for our understanding of atoms are staggering. If particles can move backward in time, if all electrons might be one electron, if particles are just waves in fields, if they don't have properties until measured, then what is an atom? Feynman's answer in his last interview was humble and profound. An atom is a mathematical structure that lets us predict observations. It's a model that works extraordinarily well. But we shouldn't mistake the model for reality itself. Reality might be far stranger than any model we can construct. Let's talk about measurement, which Feynman called the central mystery of quantum mechanics. Before measurement, and particles exist in superposition, multiple states at once. Measurement causes the wave function to collapse, forcing the particle into one definite state. But what counts as measurement? Does it require a conscious observer? Is there something special about consciousness that collapses wave functions? Feynman was deeply skeptical of this idea. He thought consciousness was probably irrelevant, that any interaction with a macroscopic system counts as measurement. But this creates its own problems. Where's the boundary between quantum and classical? Atoms are quantum. Molecules are quantum. At what point does a system become large enough that superposition breaks down and things have definite properties? Feynman admitted in his interview that nobody really knows. There might not be a sharp boundary. Nay, the classical world we experience might emerge gradually from quantum weirdness through a process called decoherence, where interactions with the environment effectively measure the system and destroy superposition. This means that even macroscopic objects, even you and me, are fundamentally quantum. We're just so large and interacting with so many particles that quantum effects average out and we behave classically. But in principle, you exist in superposition. All possible versions of you are real until the universe forces you into one definite state through interaction with your environment. Feynman found this interpretation troubling, but more honest than pretending there's a magic line where quantum mechanics stops applying. Another contradiction Feynman discussed involves time. In classical physics, time flows forward. Cause precedes effect. But in quantum mechanics, the equations are time-symmetric. They work just as well running backward as forward. Feynman's path integral formulation says a particle considers all paths through space-time, including ones that loop backward in time. This suggests that at the quantum level, our intuitive understanding of causality breaks down. Effects might precede causes. The future might influence the past. Experiments on delayed choice show this isn't just theoretical. You can change what you measure about a photon after it's already passed through an experimental apparatus, and it will retroactively change how the photon behaved. It's as if the photon knew what measurement you would eventually make and adjusted its past accordingly. Feynman emphasized that this doesn't allow communication with the past or paradoxes. But it does mean that time at the quantum level is nothing like our everyday experience of time's arrow. For atoms, this means that the electron orbits we visualize are completely misleading in another way. The electron doesn't move through space over time. Its state encompasses past, present, and future in one mathematical object. Asking where the electron was a moment ago might not even be a meaningful question. The electron's existence is smeared not just across space, but across time. Past and future are woven together in ways that make our mental image of particles moving along trajectories fundamentally wrong. Feynman also talked about quantum tunneling, where particles pass through barriers they shouldn't be able to cross. An electron doesn't have enough energy to escape an atom, yet sometimes it does anyway, appearing on the other side of an energy barrier. From a classical perspective, this is impossible. The electron would need to borrow energy it doesn't have. But from a quantum perspective, the electron is a wave, and waves can extend through barriers. There's a small probability amplitude on the other side, and sometimes the electron is found there. This happens in atoms all the time. It's how radioactive decay works. The particles in unstable nuclei tunnel through the energy barrier, holding them in. It's completely random, governed only by probabilities. There's no hidden mechanism determining when a particular atom will decay. Feynman emphasized this randomness is fundamental, not just ignorance on our part. God does play dice, and atoms are inherently unpredictable. We can know probabilities, but never certainties. In his final interview, Feynman talked about his philosophy of science. He said the job of physics isn't to tell us what reality is. It's to give us models that predict observations. If a model works, if it makes accurate predictions, then it's a good model. But we should hold it lightly, always ready to replace it with a better model if one comes along. The model is never the territory. Quantum mechanics is the best model we have for atoms, but Feynman freely admitted it might be replaced by something even stranger in the future. He gave the example of his own Feynman diagrams. These diagrams show particles exchanging force carriers, like electrons exchanging photons. They're incredibly useful for calculations. But Feynman warned against thinking they represent what's actually happening. They're calculational tools and visual aids for keeping track of terms in a mathematical expansion. Nature doesn't actually follow the diagrams. The diagrams are our way of organizing our ignorance into something we can work with. This humility, this recognition that our best theories are still just maps and not the territory, was central to Feynman's worldview. So what was Feynman really saying in his last interview? He was saying that atoms are far stranger than anything we can imagine or picture. The classical image of particles with definite properties is wrong. The quantum reality involves superposition, entanglement, wave-particle duality, virtual particles, field excitations, and time symmetry. All of these contradict our everyday intuitions, and beneath it all, Feynman suggested, might be something even stranger that we haven't discovered yet. He told a story about how each generation of physicists thinks they've finally figured everything out, only for the next generation to discover something that overturns it all. Newton thought he had the final answer with classical mechanics. Then Maxwell showed light was waves in fields. Then Einstein showed space and time are relative and gravity is geometry. Then quantum mechanics revealed the probabilistic nature of reality. Feynman expected this process to continue. Whatever we think we know about atoms today will probably seem quaint to physicists 100 years from now. But here's the beautiful part. Despite all this uncertainty, despite admitting we don't really understand what particles are, quantum mechanics works. It's the most successful scientific theory ever created. We can calculate the properties of atoms to incredible precision. We've built technologies based on quantum mechanics that literally change the world. Computers, lasers, nuclear power, MRI machines all rely on our quantum understanding of atoms. So even though Feynman said we don't understand it, we understand it well enough to harness it. This is what Feynman meant by useful fiction. The atom, as we describe it, isn't real in a naive sense, but it's real enough to predict observations and build technology. Maybe that's all we can ever hope for. Maybe reality at its deepest level is fundamentally beyond human comprehension, and the best we can do is create models that work within certain domains. Feynman seemed at peace with this limitation. He found beauty in the mystery rather than frustration. In his last interview, in knowing he was dying, Feynman reflected on his life's work with both pride and humility. He was proud of what physics had accomplished, the incredible understanding we've gained. But he remained humble about how much we still don't know. He said the universe is under no obligation to make sense to us. Our brains evolved to track prey and avoid predators, not to understand quantum mechanics. The fact that we can understand anything at all about atoms is miraculous. He ended the interview with advice for young physicists. Don't believe what your teachers tell you just because they're authorities. Question everything. Do the calculations yourself. Think deeply about what the mathematics actually means. And most importantly, be honest about what you understand and what you don't. The path to wisdom, Feynman said, and begins with admitting ignorance. We teach quantum mechanics as if it's fully understood, but it's not. Generations of students graduate thinking they understand atoms when really they've just memorized recipes for calculations. So what should we take away from Feynman's final contradictions about the atom? First, that reality is far stranger than our everyday experience suggests. The solid, definite world we see is an illusion created by our senses operating at large scales. At the atomic level, nothing is solid or definite. Everything is probability and potentiality until collapsed by observation. Second, that our mental models and pictures are always inadequate. We can't visualize quantum reality because it doesn't work like anything in our visual experience. Third, that mathematics is our best tool for understanding the quantum world, but even mathematics might just be a map and not the territory. The equations work, but what they represent might be beyond human concepts entirely. Fourth, that uncertainty and probability are fundamental features of reality, not just limitations of our knowledge. The universe, at its deepest level, is inherently random, and we need to make peace with that. And finally, that science is an ongoing process of discovery, not a collection of final answers. What we know about atoms today is better than what we knew yesterday, but it's not the final word. There are deeper levels of reality waiting to be discovered, stranger than we can probably imagine. Feynman's legacy is not just the specific discoveries he made, but his approach to science, his insistence on honesty, his comfort with uncertainty, and his joy in mystery. The atom, as Feynman understood it, is not the simple picture you learned in school. It's a quantum entity that defies visualization, that exists in multiple states until observed, that's entangled with everything it's ever interacted with, that's really a ripple in quantum fields extending throughout space and time. It's something that works according to precise mathematical laws, but whose ultimate nature remains mysterious. And according to Feynman's final interview, anyone who tells you they fully understand it is either lying or hasn't thought about it deeply enough. That contradiction between our incredible predictive power and our fundamental confusion about what it all means is the heart of quantum mechanics and the heart of what Feynman wanted us to grapple with. The atom is both known and unknowable, and that's the most profound contradiction of all. What makes Feynman's perspective so powerful is that he refused to hide behind equations. Many physicists are content to say the math works and leave it at that. But Feynman pushed further. He wanted to know what the math actually meant about reality, and his honest answer was that we might never fully know. The equations describe patterns of observation, but they might not describe what's really there in any meaningful sense. This distinction between description and reality is something we rarely acknowledge in science education. We teach students to calculate, to predict, to apply formulas. but we rarely teach them to ask the deepest question. What does this mean? Consider how this changes everything about atoms. You've been taught that atoms are the building blocks of matter, that they're made of protons, neutrons, and electrons. This makes it sound like atoms are things, physical objects with definite structure. But Feynman suggests this is fundamentally misleading. An atom is better thought of as a set of mathematical relationships. It's a way of organizing information about what we'll observe when we interact with matter at tiny scales. The atom itself might be more like a thought than a thing. This doesn't make it less real in practical terms. It works. We can manipulate it. But it challenges our basic intuitions about what existence means. This realization extends beyond physics into philosophy and the nature of consciousness. If atoms aren't definite physical objects, if they only become definite when measured, then what does that say about the things made of atoms? What does it say about us? Feynman didn't go far down this road, being primarily concerned with physics, but he acknowledged the question was worth asking. The observer and the observed might not be as separate as we assume. The mind that observes atoms might participate in creating them. This isn't mysticism. It's what the mathematics of quantum mechanics actually suggests. The strangeness runs all the way up.